Okay, I'm going to start the second prep with just a couple of suggestions because when you answer a question on pedigrees, there will be 1 point for the correct answer of mode of segregation. There will be 2 points for the reasoning. And so I want to be super clear about the kind of reasoning I'm looking for. Things like skips a generation and seen in every generation, or in the case of X linkage, which we haven't looked at yet, but more males have it. These are general and vague answers that are not specific to the pedigree. Saying skips a generation is not it's just words, right? It's not a real reason. So rather, what I would expect to see is, the grandfather has this condition, individual 1-2. It is not observed in his daughter 2-4, but her daughter 3-6 has it, and because of that pattern, we can say it's a recessive trait, right? So I'm looking for really specific features of the trait that you're talking about. And the truth is, you can make a pedigree for a recessive trait where there's never any skipping of generations. We're seeing it, because there's a lot of homozygosity and lots of carriers in the family, and it being seen in every generation. That could be recessive. It doesn't have to be a dominant trait. So seen in every generation isn't specific, but every child who has the condition has a parent with the condition. That is specific. And I hope that will be helpful, because I suspect sometimes students do know the reasoning, but they don't express it clearly. And of course, we are scientists, Emily and I, and we're looking for evidence. And we can't just assume that unless you provide us the evidence that you know. So that's really our aim, is collecting evidence that you understand the material and that you can explain it clearly. Okay, so here's, I'm going to tell you sometimes, here's an autosomal trait, tell me if it's dominant or recessive. And here's some key things. One of them is that you have affected children and the parents are not affected. Okay, so there's, it's recessive. So you could say affected children and unaffected parents. It would be better to specify the particular individuals and so on. And there are things that you might think of where you think, oh, it could be a new mutation or something. But it's not very likely. So we want you to really just focus on, we don't want you to look for those other possible explanations. When you're thinking of a pedigree, think that it is either autosomal or X-linked or possibly Y-linked, and that it is either a dominant or a recessive trait. So, don't be looking for these other things. But even if it was a novel mutation, there are new mutations that pop up sometimes in a family, but they don't show up in like two different individuals, right? So that would be rather unlikely. Okay. So another thing to notice in this pedigree is that we have consanguineous marriage here. So these are cousins. They have the same grandparents, and so they are heterozygous for a condition that they must have inherited that recessive allele from one or the other of the grandparents. We don't know which one. We know their genotypes. We know the genotypes of the individuals that are affected too, because they must be homozygous. We know it can't be an X-linked trait, because if you hadn't been told it was autosomal, because here's a daughter and her father doesn't have it, and so it can't be an X-linked trait. And we can go in and we're going to make assumptions. So we're going to assume anybody marrying in to the family is homozygous normal, unless we have evidence otherwise, and we don't. We know that this individual must have inherited this recessive allele from that parent, and this individual must have inherited her recessive allele from this parent, okay, because they would have inherited it from a common ancestor. So we can fill in that much, but notice that for most of the individuals, if they're showing the dominant phenotype, we don't know what their genotype is. We just have to use that slash notation. Now, for another case here, again, I want to point out, it's possible that this would be a recessive trait. So everybody who has it is, homozygous recessive, and then every single person who marries into this family has to be a carrier, right? And I will usually specify in my questions to you that it's a rare trait. If I say it's a common trait, then all bets are off. But for a rare trait, it would mean that there was if this is found 1 in 100,000, then there's a 1 in 100,000 times 1 in 100,000 times 1 in 100,000 chance that that these heterozygous individuals will be marrying into the family, right? So it's not impossible, but it's really unlikely. Notice that every child who has the condition has one affected parent. Every single, like everybody for whom we know their information. And so it's a dominant condition. And we see, for example, here's a case where a father, if you weren't told, like I think I mentioned to you already that it's autosomal, but if you weren't told that, you could tell it is too, because here's father passing it on to his son and to his daughter, and that's classic autosomal, because fathers don't pass their X chromosomes to their sons, and they don't pass their Y chromosome to their daughters, and so therefore the only interpretation here is autosomal dominant. And when you make that determination, you can fill in all the genotypes, because anybody unaffected is homozygous for the recessive allele, and anybody that has the condition is affected has the dominant allele and will be heterozygous. We know these people are heterozygous. First of all, a lot of dominant alleles have much more severe phenotypes if they're homozygous, but also in every case an unaffected person is one of the parents, so there's no question what their genotypes are. Okay, and then notice also, in the explanation over here, I scrolling over on this side of the screen, but it indicates individuals and it identifies them with their number designation, and that's the right way to give the reasoning for that. Okay. So we'll look at X-linked traits. X-linked are almost easier in some ways because we see specific, sex-specific patterns in the way the traits are passed. Now we sometimes do, I'm going to change color here, we sometimes do see more males showing the trait in the family than females. And it's, if we have an affected male in a family, so a male who, say, is colorblind, which is a common X-linked trait, you don't usually see that trait in the sons or the daughters of that male, because the daughters are going to be heterozygous. They will have gotten only one of the father's alleles and then one of the mother's, so they're going to be heterozygous. But the sons are not going to show it because they don't get their X from their father, right? And so, but if we see affected females, if you have a mother who's got the trait, this is a really badly drawn pedigree. But if we saw just one male with it, for example, we'd have to go, okay, this must be an autosomal recessive trait. And just by chance, just this one son is getting it, the father must be heterozygous. But if we, and the reason is because if this is X-linked recessive, both the males will have it. The mom only has recessive alleles to pass on, and the males only get their one X from their mom. So whatever she's got, that's going to dictate what their genotype is. So this is a really common pattern in X-linked recessive. Notice this isn't skipping a generation. So again, that's not the right kind of reasoning. It's more about the specifics of the pedigree. And in this case, this pattern, it could still be an autosomal trait. It could be X-linked dominant with just the weird likelihood that that it only passed to males and not females and so on. But if we're looking just at the pattern, what you would say is the most likely explanation for this is that this is an X-linked recessive trait. Mom is homozygous, right? And that explains why her sons have it, all of them, and none of her daughters, because the daughters would be heterozygous. They get the good X, the one without the disease causing allele on it, from their dad, right? Now, if you make this interpretation and then here's some more information, 2 more children are born in the next few years, and now we have this, you have to change your interpretation, because we have a son that didn't inherit it and a daughter who did. So this is just, I know I'm kind of blathering on a lot about it, but I really want to try to avoid people getting I don't know, confused. So people get so addicted to the idea of just getting it right, At this point, with only this information, the right way to interpret is X-linked recessive. That's the kind of pattern. But as soon as you have additional information, it's okay to change and say, oh, this must be an autosomal trait. And then even though it's not as likely, but we have this, it can only be this, right? It has to be an autosomal recessive trait. So just, we'll go through some more examples and hopefully it'll be clear. In the case of X-linked dominant, one of the key things is males who have the condition transmit it to all their daughters. So all the daughters have to have it and none of the sons, right? That's because males only have one X, and all their daughters are going to get that X, so they're going to all get the condition. But if the mother isn't affected, and the sons will not be affected, right? They don't get their X chromosome from their father; they get it from their mother. And then if you have a female that has it, she can pass her X chromosome to her daughters and to her sons, right? And so there's no sort of sex specific if it's the female who's affected, but if it's the male, we can see a particular pattern. And we're always looking for those kind of patterns. So I want to give this example. I just was listening to a podcast yesterday, and somebody had written in and said that color blindness is only expressed in males, which is absolutely incorrect. It's more common in males, though. Okay, it's found on the X chromosome, and it's a recessive allele, and it's recessive to the wild type allele for color vision. And there's several different genes, but this is the commonest one, the red-green color blindness allele. And so males only have to have one mutant copy in order to be colorblind. And one dominant allele, one of the normal vision for normal vision. Females would have to inherit 2 mutant alleles. So her father would have to be colorblind and her mother would have to be heterozygous. So it's much less common, but I've had several female students over the years that were colorblind. Females can also be heterozygous, right? They can have normal vision but be a carrier. Half the sons on average would be colorblind, or they can be homozygous normal. So this is the kind of proper notation for X-linked traits. And I threw this in because I just think this is really interesting. There's these websites you can go to. These are some of the patterns that are used when they're testing children to see if they're colorblind or not. And I have to say, I find this one the hardest one to make out. But there's also sites you can go to, and they show you what it looks like to be colorblind. And that's, if you're trying to make lecture notes and you want to make sure that the things you're putting up for contrast really do help everybody see the contrast, then it's a very useful site to go to. And if you're just curious, you might want to take a look at it. Okay, So here's a couple of examples of X-linked recessive traits. So this one, um, the mother would be heterozygous, right? And the dad would have the dominant allele. And then she passes on the recessive mutant allele to some of her sons, but not to all of them. Could this be autosomal? Yes, it could. But if it was autosomal, we would have to assume both parents were heterozygous. So they'd have to both be carriers for the recessive allele. And so this requires the fewest assumptions, because we can assume that mom is heterozygous, but we don't have to make that assumption about dad. And if we're talking about rare traits, we prefer a case where just one parent has to be a carrier rather than the others. Okay. This is something to watch for too. Here's a female who's affected. Notice this isn't skipping a generation. All her sons have it, but none of her daughters have it. And so that's a common one for X-linked recessive. And here's another one. Here's a case where a grandfather has the condition. His daughter and son are not affected, but his daughter then has a son, but not a daughter with the effect. And so when you see this going from grandfather to grandson through a daughter, now it looks like a bullseye, then that would, we would say that our most likely mode of transmission should be X-linked recessive, because then if it was autosomal, this guy would have to be a carrier. We don't want that. We don't have to make any assumptions at all about it. However, if this was a male and we saw a grandfather to grandson transmission, but it was with through a father instead of through a mother, then it can't be X-linked, because of course the X chromosome passes from grandfather to daughter and then to grandson, right? But the X's don't go that way if this is a guy. Hopefully that's clear. And then for X-linked dominant, mothers pass to both kids with equal frequency. And so for X-linked dominant, you don't have any information if it's a mother who has the trait and is passing it to the children. It would look exactly the same if it was autosomal dominant. But that is, if you had other evidence of X-linked dominant elsewhere in the pedigree, then you would know for sure. But that's how it would segregate. And for an affected father, all the daughters, but none of the sons would have it. And when you see a pattern like that, and you don't have any other evidence elsewhere in the pedigree that is contradicting it, then we would say it must be an X-linked dominant trait. Okay, and so recessive, you see recessive because we have unaffected parents with an affected child. You see it only in males, but it isn't just that it's only in males. It is that it goes from the grandfather through the female to the grandson. Okay, and it's unlikely that this would be autosomal recessive because this individual would have to be a carrier, right? And this person would have to be homozygous. If we can make him hemizygous, it's easy. Okay, and then in this case, X-linked dominant. So this is a larger scale pedigree here. If we're only looking at this part, we aren't really sure if it's autosomal or X-linked, but because we have this information plus this information, all of this points to X-linked dominant. Dad passes it to all his daughters, but then the daughter passes it to both males and females, because that is how X-linked traits are segregated. Okay. So, and as it says here, you can't always completely rule out every, if you wave your arms and make lots of assumptions, you can make autosomal recessive work for this. You could make something else work. But you could make X-linked recessive work if you just assume that, she's heterozygous and these ones happen to get it and these ones don't, and so on. But so I may ask you, tell me what all the possible modes of segregation are, but tell me also what the most likely one is. But this is usually the one I'm interested in. The answers for these are often different. So you want to be careful when you're reading a question, because if it says, is this, like with a multiple choice, is autosomal dominant the most likely, right? And it wouldn't be. Is X-linked recessive possible? Yes, it may be possible, but it's not the most likely, right? So just pay really careful attention to the wording of those questions.